Hi everyone, and welcome to this session on 5G security architectures. My name is Munib Shah, and before we start, I just want to give a small introduction about myself. I'm a SP security architect, and I work in the APJC region. I help my clients design a security roadmap, especially to the ones who are moving to the cloud or who are becoming cloud native or their vision is to become cloud native. I'm currently working on the Rakuten Mobile project in Japan, and I'm a fan of football, also a big fan of Lionel Messi. So, for those of you who are also FC Barcelona fans, you will be able to connect the dots between 2 and 3 going to the agenda. So, many of you will agree that 5G security cannot be covered in 25 minutes. Right, it's huge. What I've done with this presentation is I'm building up to a philosophy. So items 1, 2, 3, 4 is that build up towards a philosophy, which will present it on slide 5, which I hope will be your takeaway from this session. So we're going to start now. Understand that there is varying background of people who are joining this session. So I'm going to start with 4G, 5G architecture basics of what is the difference between the two. We're going to quickly go through the use cases, the 5G threat surface, and then we're going to spend a lot of time on the attack scenarios and mitigations. That is what will build up to the final slide, which is the recommendations. Now, to start with, 4G end-to-end architecture. If you look at the end-to-end 10,000 foot view of the architecture, you'll see that you have RAN on the left side. This is where your endpoints connect. You have eNode Bs, which is your antennas, which connect back up to the backhaul. Then you have the transport, which is where all the cities and states are connected using these routers. These are your aggregate routers, which generally run protocols such as MPLS or BGP and the new protocols such as SRv6. Then you have the packet core, which most likely you will have it in a central data center somewhere or multiple central data centers, which then connect up to the internet. Now, what is changing with 5G? From the left, the endpoints. It's not just mobile phones and tabs connecting to the internet. It is much more. It is smart houses, it is your watches, your cars, which connect through the service provider to the internet. The other change that happens is your antennas. So all the innovation that has gone into antennas is brought into 5G with G-Node Bs. It's not eNode Bs anymore. And then you're also using latest spectrums, millimeter waves, and so forth. And the third one, which is also a major one, is the edge data centers. With 5G, what you now have is distributed data centers where you have a big central data center and then smaller ones which are closer to the users to meet some of the use cases that we will talk about in the next slides. So the other split that is important for this presentation, because I'm going to talk about this a lot in the future, is that your RAN side. So earlier, it was all one big unit. But now, with Open RAN, which has been becoming quite famous in the last couple of years, it's also split. Your RAN is built into now smaller components, which now you have architectural options. You can place them at different parts of the network. The most widely used one would be you'd place your DU, which is your distributed unit that converts signals from your RAN to something that the core understands. You'd place it closer to your radio unit, and that piece is called front haul. You have your DU and your CU, and that piece, the transport between the DU and the CU would be called mid-haul, and most of the times you place this CU in the edge or sometimes in the core. And then you have the UPF function, which is the actual function which moves traffic out or which processes your traffic in the core, which you would place in the core. But many times you would also, or sometimes you would place it closer to the CU for some of the use cases. There are different deployment models of 5G. It is not completely 5G core and 5G transport. What it is, many times you will see of the different options, the most widely used one is 3x. What that means is most of these operators, what they use is they upgrade the antennas. So they're using millimeter waves, they're using the latest frequencies, but their core is still 4G. But you're not completely realizing the full use case which 5G provides you until you move completely to 5G core. And that's where service providers are moving to. But looking at the trends, and because you have to build all of those edge data centers and connectivity and IoT has to mature, you're looking at 2 to 4 years until that happens. And until then, we're going to be in this hybrid model where you'll have probably a different core and 5G network transport. to the next one. So use cases, this is one of my favorite slides, but cognizant of time, I'm not going to spend much detail on this. At a very high level, you have three major use cases. You have enhanced mobile broadband, where you're seeing high speeds, gigabits in seconds, 3D video, and so forth. Then you have ultra reliable, low latency communication. Now, this is URLLC, where you have use cases such as self-driving cars, industrial automation, remote surgeries, and so forth. And the last one is massive machine type communication. Now, this is the one where you have your traffic lights talking to your cars, making sure that they're stopping at a red light. And those kind of use cases will come in with machine to machine type communication. So obviously, with all of these features, with all of these benefits that you get with 5G, you're also expanding the threat surface. And that's what we're going to talk about here. The threat surface. Now, there is a very good, a very detailed white paper that Cisco has, and there is a reference I've put here in the slide, where you can look at. So what they've done in the white paper is they've split 5G into multiple components. You have the endpoints, the RAN, the core, the edge, and then the access towards the internet. And then they have very clearly defined what are the threats that can occur at these different components. Now, we can't get into each of these in details with the time that we have, but at a very high level, DDoS is kind of the one that with 5G is expected to grow because of IoT and man-in-the-middle attacks and so forth. If you go through a lot of news items that come out, you will see that these are real, right? It's not just on paper. Many of these attacks happen year on year, and most of the times, what we've seen is when an adversary is able to get into the network, they would stay there. They would stay there and collect data because of the quality and the richness of data that you get in a service provider, right? You get data, you get subscriber data, you know what subscribers are doing, and you're able to use that to influence public opinions, you're able to use that for espionage and whatnot. That is what we're looking at protecting when we're talking about protecting the threat surface of 5G. Now, that covers the first 3 points. Very quickly, to just give you an overview of what 5G is, what we're looking towards, and what is the threat surface. What we're going to do in this presentation is we're going to look at some of the scenarios which are most likely to occur, and we're going to go through them, thinking from the mind of an attacker to see how can we get into a network or how can we expand inside the network as a threat. And then what are the mitigation features you can put in place so that you can stop bad actors from coming in, right? So we'll start with the perimeter. So what we'll try to do is, this is a high level diagram of the architecture. So what we want to do is we want to breach the perimeter and we'll try to get in. The first place to do this would be your front hall. Your front hall is, and why did I choose the front hall, or why is this a clear target to start with, is because there's tens and thousands of these across country, right? This is where your towers connect. And with 5G, you're going to have a lot more towers because it's smaller in size, millimeter wave, so you need more to cover more area. These are going to be on rooftops. These are going to be on shared rented spaces, which means that access to them is not controlled completely by the service provider. So let's say we find one and we're able to bust it open, right? What would we find inside these cabinets? More likely than not, you will find something like a switch or and a compute, right? You would have a switch which has ports or a router which has ports which connect back up to the RAN, and then you have the compute where your workloads may be residing. Let's say you're an end-to-end virtualized service provider, you might have virtual workloads on that compute. Now, we have the security, we've had the security in our networks for decades, at least our switches, which is a very simple control. It's port security, dynamic inspection, and trusted hardware. But the important thing to remember here is that you have tens and thousands of these devices. So you want to have some sort of automation to make sure that when they come up, either you build automation inside, so you make sure when they come up, they have the security in there, or you have some sort of automation, network automation running like Ansible or some other controllers, which make sure that you're doing this and configuration changes do not affect or leave holes in these devices because they're exposed out there. The other thing is on the compute. Now, what we are seeing mostly closer to the RAN is going to be, you would have a component such as a VDU on these compute. So what you want to also make sure is that someone doesn't corrupt that software, because even though they're not able to connect their network piece or their equipment to the network, they may be able to corrupt the software that is on top of it or install their own software to connect to your network. And that's where zero trust comes. Zero trust is nothing but ensuring that any device that is communicating on the network has a minimum level of trust associated with it. Easier way to do this is with certificates, but your DU vendor may have other ways of doing this. So you need to talk to your vendor and see what are the different options that you have, but you want to make sure that at least there is some sort of a check of security, a trusted boot or certificates, so that before they come into the network or they're giving configuration from the network, they prove themselves to be secure or they prove their identity before coming in. The next one is IPsec tunnels. Now, 3GPP, which is the standards body that manages 5G architectures and then gives suggestions, they're the ones who create the standards for 5G. They recommend to have IPsec tunnels on this transport. Now, it depends on different operators of how they look at this. If you are running on a lease line between DU and CU, then it's recommended to do this because you're going to be over transport which is not controlled by you. But if you have transport which you own and it's trusted, you can skip it. But anyways, best practice would be to have end-to-end IPsec encryption. If your CU and your DU vendor doesn't support it, you could have something like there is a dedicated device for this called Sec Gateways, which is basically nothing but VPN concentrators. This is where your DUs, all the DUs across, can terminate their VPNs on the CU or even end-to-end towards the core. So now you have zero trust protection, identity protection, but at the same time you also have transport protection for confidentiality and integrity, right? That's how you protect your front haul. So I've made sure that no one can enter. Let's say I've done this on my DUs, I've done this on the front hauls, so I've protected that side of the network. What next, right? Is there another hole in the wall where we can enter and try to enter the core? And the answer to that is yes, there is, and it's called roaming. And why is roaming a hole in the wall? Is first, before we get there, is just on the architecture of where roaming is placed. And why is it important is because it has direct access to your core. How it works is, let's say I'm in my home network, I'm trying to roam on to a different network. The moment I leave my network, I enter a roaming network. My traffic eventually ends up to my home network through the partner. And when that happens, it happens on different interfaces, which are signaling interfaces. And it used to be SS7 before, now it's GTP and diameter. Many times the controls that are put on these interfaces are inadequate. Many times we've seen that. And the impact that it causes, right? The first one is fraud. And if you look at the number, it's $38 billion a year. That shows you that how juicy this interface is for attackers, right? A lot of times fraud gets undetected because service providers have a lot of bills, so it gets hidden in those bills, but it is there. Fraud is a very well-known abuse of this system that we've seen in the past, and it keeps happening. Denial of service and disruption of billing is another thing that you can carry out on these interfaces. So how do you mitigate them, right? 3GPP has defined with 5G, they've actually come up with a device called SEPP, Security Edge Protection Proxy, which helps you to do that. And what it is it basically protects that signaling on that link. It creates an authentication system where the operators authenticate themselves before sending traffic. There is application level security between that transport. There is a new protocol that they've defined to protect this interface. So they know this, everybody knows this, they're aware of this, and they are protecting it with new security features. Although one thing to note here is this is 5G to 5G, right? If you're roaming from a 5G network into a 5G network, what happens if you're roaming from 4G? That's where you have to be careful as well, because if you're in a 4G network and you're trying to go to a 5G network, 3GPP, SCPP device will not come in the path. And you might still have open holes where people are able to access your core. And that's where you need to implement GTP and diameter firewalls. Most likely service providers will have this already. But one other thing to note here is many of these GTP firewalls, many of the vendors claim that they are GTP compliant, they support GTP filtering, but unless they're able to show compliance with GSMA FS19 and 20, they won't be effective with all kinds of attacks. GTP is a very complex protocol. It has location-based filtering, IMSI values, a lot more information. So for a firewall to be able to protect against that, it has to be compliant to the standards as well. So for the technical folks on the call, these are the specific interfaces for reference only, where you can actually put those controls, the S6, A, and S8, and all of that detail is. Now, good, we're done with the perimeter, right? At least relatively secure. We can never say it's always secure, but relatively I've found my gaps, I've secured them by making sure I have controls. What else can I do? So I've gone through confidentiality, I've gone through integrity. What else I can do is availability. So that is where DDoS comes in. Now what you can do with DDoS is I can try to attack the network from the IoT threat surface that is now available to me, right? I can use those devices to get into the network, and the first place where I can get in most likely is going to be your DU and then go on to your CU. That's where I impact the DU, I find out vulnerabilities on the DU, or I'm not even trying to go there, I'm trying to go somewhere else. I could be trying to go to my edge, I could try to disrupt my edge services, and if I do that, then my attack radius or my impact radius is a region. If I'm able to somehow do DDoS attack on the core, which I have the capability now because of the number of devices that are available to me, then I can impact the core. And the radius of that impact is going to be all subscribers. And I can even use the whole infrastructure, right? I can go through the core to the internet. So I'm not affecting you, but I'm using your infrastructure to go somewhere else where your reputation is now at stake. Now, how do you protect it? There are three major mitigation mechanisms that you can apply to mitigate against DDoS. You can reduce risk and eventually mitigate. And what are those? The first one is slicing. Now, this is something that comes inherently with 5G. With 5G, you are virtualizing your core, right? Your packet core is virtualized. Many operators are doing end-to-end virtualization. What that helps you do is slicing. And what slicing is, you isolate and split your network into multiple resources, and you assign those resources to different use cases. So your gaming can have a different slice, your IoT can have a different slice, your packet core can have a different slice. What that helps you with is if someone attacks your IoT slice, if they try to get into your IoT packet core, your gaming is still functioning, or your packet core, consumer packet core is still functioning at the same time. One thing that, again, slicing is up to the operator to do. So operators can find their own ways to slice, but it's always recommended to have dedicated devices per slice. And if you can't do that, then the next best practice would be you isolate the VNFs or CNFs or the devices that you need for data traffic and critical session management traffic or even access management traffic. That's what we've done here. So that if there is an attack on these elements, the other signaling is still fine. You don't see a lot of data towards those elements, but the elements which see a lot of data, you separate them by isolating them on different containers or different virtual machines. Now, one thing to note here, as you can see, we have sliced it, but you still have a common virtualization structure. You still have a convergence point, which is virtualization. We'll talk about that in the coming slides. Now, the other mitigation that you can add is throttling. Throttling is a way where you can manage sessions if the number of sessions are increasing. And a lot of white papers have been published on this, that the most efficient place to implement throttling is your CU, because it sees a lot of requests. Radio control requests are seen by the CU, so you can then manage sessions if they go above a specific threshold. Now, your CU may not have capabilities to detect anomalies or analytics algorithms, but what we say in the least is it should be able to take commands from, let's say, NetFlow collector or a device such as StealthWatch, which does anomaly detection using machine learning, so that when it directs the CU to adjust thresholds, it's able to do that dynamically. The final one is anti-DDoS, and this is the most recommended one as well, where you have dedicated resources, dedicated devices on different parts of the network to protect from DDoS attacks. So you want to protect your edge data centers, you put your DDoS protection on the mid hall, you want to protect your core, you put it on the back hall, and you want to protect the internet, your reputation, you put it on the link towards the internet, which is the N6 interface in case of 5G. So the best way, again, the other best practice here, because you're going to have a lot of these edge data centers eventually. So it's good to have one single place of control, which is maybe an anti-DDoS controller, which helps you manage this policy from a single pane of glass. So that's it, right? So we've done with the perimeter, we've done with confidentiality, we've done with integrity, done with availability. But what if they get in, right? I'm talking about a scenario where they find a hole in the perimeter and they come in. So this is actually from one of my favorite movies. So let's say they come in through a tunnel, they come out, and now they're inside your core or any other part of your network. How do you protect yourself there? And that's where virtualization comes in. And why we want to talk about virtualization is because it's a growing concern with a lot of providers. They're virtualizing, but then they're also opening up a new threat surface, which we're going to talk about here. And we'll focus on containers because a lot of operators are looking to move towards containers. They see benefits, and which is there, like containers provide a lot more benefits than virtual machines in terms of efficiency, but they also have a good, juicy threat surface. You have kernel escapes, later movements, you have insufficient network policies, access management, resource management, and a lot more. What I'm going to cover in this presentation is more about the first two and the controls to protect the first two, because they're mostly going to cover the rest of them as well at a very high level. A very simple explanation of this one. Let's say you have a container from a slice which gets infected. Kernel escape is nothing that they will try to first get into the kernel. And why would they would do that is because kernel is shared. That means they can just very quickly enter another slice. And that's the risk here, right? You have slicing, you have isolation, you have different containers, but if your kernel is not isolated, you're still leaving a hole for them to enter or escape from one slice to another. Protection against this, and Kubernetes provides this and many other providers as well, something called pod security policy, which basically ensures that your pods or containers, before they come up, they have minimal security requirements that they meet, and those you can meet with security context. Security context, you can define what sort of isolation works. It has to work for your applications. Your applications have to be compatible with that isolation, as well as your kernel has to be supporting some of those isolations. So you define those in the security context and enforce it with pod security policy to make sure that your kernel is secure from resource exhaustion and anything else that a container can affect the kernel with. The other is simple east-west traffic, right? Let's say I have non-IT applications that get impacted from the internet. What could happen is it could get spread internally. And with Kubernetes, these are virtualization container structures. Why this is well known is because they have their own way of networking. Many times inside the cluster, most of the pods will share the same IP space, which means you can spread easily across unless you have some sort of a control in place. So you can go from non-IT apps to IT apps unless you have isolation. And how do we do that? At least with Kubernetes and containers, is we do some sort of namespace isolation. Now, what namespace isolation is, you do it with network policy. A lot of CNIs like Calico or Weave, or even service meshes like Istio, allow you to manage pod-to-pod connectivity. So only specific connections that you specify are the ones which are able to communicate. Otherwise, you're not able to communicate to the rest of the cluster. So knowing this, we move on to the last piece, which is protecting the core. Now, we know virtualization, we know what it can do, and there are controls which it provides, and there are threats which it comes with. Knowing all of this information, how do you protect the packet core? Good thing about 3GPP is it has security embedded. That means the network functions, especially on the service-based architecture interfaces, when they talk to each other, they need to have, as long as they are 3GPP compliant, which mostly they should be, they will have integrity, confidentiality protection, because they use TLS and OAuth. So they communicate, they mutually authenticate between each other, and they use tokens to communicate between each other. That is what 3GPP provides. But how do you add layers of security on top? And for this, there's a really good 3GPP paper that has been written, which designs a trust model around these elements. So you define your crown jewels, which could be your UDM or your ARPF, and then you define controls around it, because you know that those are the most critical ones and you want to protect them not just with one layer. You want to do defense in depth, so you add more layers. And how do you add more layers? Is with network isolation, kernel isolation, firewalls in places where you would need those controls, IPsec tunnels, or even ACI contracts from a physical infrastructure perspective. So you add more controls to those. And once you go out of the layers, when you're crossing from one trust level to another, you can manage and add more controls as needed by the core, depending on how your platform is suited. That is all I have to talk about from a attack and mitigation perspective. Now we come to the last part of it, which is the recommendation. So to do this, I'm going to go back to the end-to-end architecture slide. And as you see, this is your end-to-end. And we talked about slicing. You can configure slicing across, you can isolate environments on the same structure. What you have to be careful about here is hardening of the infrastructure. Again, we're talking tens of thousands of devices in the network. So slicing is just a configuration, right? Which means on a router somewhere, if you've not configured it properly, there could be slice escapes, which is quite possible. So what you want to do is you want to have a hardening process set up where you make sure that you constantly keep checking your configs to ensure that you don't have gaps in your configurations. You want to make sure that you have a proper identity management and access solution. You're going to have a lot of vendors access your network here. You're going to have vendors from RAN, vendors from mid-haul, vendors on the core. So you want to make sure you have a proper identity access management solution to manage their access and revoke it when needed. FCAPs, fault, configuration, accountability, performance, security, all of that in production. You want to make sure that a device is going out of capacity, you know about it before. There is fault in the network, you know about it. So all of that integration has to be set up. You want to have visibility by logging. So devices should be logging to SOC or NOC, where you see the entire network end to end. You also would need a good vulnerability management solution where you have a view of vulnerabilities in your network so you can protect against them when needed. Now, all of this, like look at the complexity of this, right? Looking at the number of devices and the number of things that you have to take care of. With the increase in network, when you increase your slices, when you increase your use cases, when you increase your edge data centers, what you're looking at is more complexity. How you can simplify it is with the philosophy of zero touch, zero trust, but embedded in your orchestration. You're anyways going to have orchestration in the network. To scale, you need orchestration, you need devices which talk to your entire network, which can spin up a slice when needed. So new instances are spun up, but what you want to make sure is when these instances are spun up, they have day zero configs, which you can do with virtualization. They have day zero configurations. They have embedded configs, which when they come up, they're already hardened. They have identity management. They're integrated with your FCAP solution. They're logging and they have good vulnerability protection. You may do penetration testing in your process, but you want to make sure all of these things are done. And what that will help you with is when you expand further, security is baked in. So you don't have to catch up with security. You can expand and your team can then focus on newer threats or newer attack surfaces that may come up with new use cases coming into 5G. That's all I had to say. I hope this has been informative for you, and I'll open it up for any questions now, please.